Hello, welcome to this session. We'll learn about the electric potentials. In the previous sessions, we discussed about the electric field vector, how to determine that for given uniform and non-uniform charge distribution, and also when we have symmetrical and non-symmetrical charge distribution. So in this session, we'll see how to determine the potential difference between 2 points if we know the electric field vector E. So the voltage is by definition the amount of energy required to move a test charge from one point to another inside electric field. So mathematically, it can be determined by just taking the line integral of the electric field vector E between 2 points. Well, here it says reference, so that is starting point. So it can be any arbitrary point in that region, but it should be consistent throughout the problem. Especially if we want to determine the voltage at this point, it means the amount of energy to move a test charge from infinity to that point. Again, if I want to determine the the potential at this point, it means that the amount of energy required to move that unit charge from infinity or from our reference point to this point. So if I say V at this point is 10 volt with respect to some reference, then when I measure the voltage at this point, it should be again with respect to the same reference. That's why it said that reference point should be consistent, or it should be constant throughout the problem. So again, if I say this is 5 volt, again, this is with respect to the same reference. If I have two difference points, then I'll get two different voltages. Then it will be difficult to compare or to take the difference between these two. For instance, how much is to move a charge from this point to this point? And then in this case, I can say 5 volts because I know that the 10 and the 5 volts are with respect to the same reference. But had it been with respect to a different reference point, then I can't even compare these 2 points. So keep that in mind. So if we know the electric field vector, then we can determine the potential or at any point in a space or in that region. And the other thing is the electric potential at a point is always independent of the path taken. There are many ways to go from one point to the other point. If I have 2 points here, then there are different ways to go from here to here. So I can show you some of the ways to go. So let's say this is A and this is B. See, as you can see, there are many ways to go from A to B, but the potential difference is independent of the path taken from A to B. Whether you go along the longest path or the shortest path, still you get the same thing. So that means over the closed path, it is 0. Over the closed path, we'll see. So if you remember, the curl of E is 0, right? That's the first basic law of electrostatic. And from Stokes' theorem, we said that E dot dl is 0 over a closed path, over the closed path. So that means the line integral of E dot dl from A to B plus the line integral from B to A of E dot dl is 0. And we know E dot dl is from A to B is a potential difference between A and B. Again, E dot dl from B to A is again a potential difference between point B and point A. So regardless of the path taken, we get the same potential. Then if we add these two, then we get 0. So it's the same as KVL, right? Sum of the voltage in a closed path is always 0. So this is that version. So this line. So E dot dl is V. So if it is over the closed path, it is just like KVL or Kirchhoff's voltage law. So on a KVL, it says sum of the voltage in a closed path is actually 0. So V is always independent of the path taken. And there is another way of solving for E. Now, in the previous slide, we've seen how to determine V given E, or the electric field vector. We can also determine E, or the electric field vector, given V. If we know the potential difference, then from that, we can also determine the electric field vector. And how do we do that? By just simply taking the gradient of the scalar potential. There is a mathematical for expression. It says the curl of the divergence of any vector is 0. So where V is any vector, and we know that the gradient of V is, in this case, is E. So that is the curl of E is 0, and this is true. And this is true. I mean, it's just to show you another way of how we get this curl of E, or how we get E equals to divergence of the gradient of V. So the curl of E is 0, that's true. The curl of the divergence of any vector is 0. That's true for any scalar function, if it is F or if it is A. For any scalar function, the curl of the gradient of the scalar function is 0. So we can also, from that, we can say that E is also equals to the gradient of scalar function V. Now we have a minus sign because, as we've said in the previous slide, the potential energy always goes from higher to lower, whereas the electric field goes from lower to higher, or from stronger to weaker fields. So it always points along the maximum rate of decrease in the scalar potential. Then if I know V, then I can determine E. And the other thing that I want to mention when we discuss about electric potential is equipotential surface. Now, if you see, these lines are electric field lines, and all diverge or emanate from positive charges or terminate on the negative charges, as you see. So given the electric field lines, we have points along which the electric potential is the same. So for instance, if I pick this point, any point along this line, along this dotted line, have the same potential, because here we have a spherical coordinate system. They all are equidistant from the center. So at that point, we know that the potential to bring, for instance, if this is my positive charge, the energy required to move this charge from infinity to this point is the same, whether I bring it to this side or from infinity to the other side. So they all are equidistant from the center. If you assume just like a sphere, so bringing the charge from infinity to any point on that surface of a sphere have the same V, or they have the same electric potential. So all these surface points are equipotential lines or equipotential surfaces, and the same is true for others. Now this is if we have only one charge. If we have 2 or 3 charges, this is a line distribution, or these are the electric field lines, and this is what you see for the equipotential surface. So on the equipotential surface, let's say on this one, again, if you go any point on this surface, we still get the same voltage. So that surface is known as equipotential surface. So they all have the same potential. So since they all have the same potential, it means that no work is done in moving a charge on that surface or along that line. So there's no need of having external energy or external work to move a charge from one point to the other point along this surface or along this line, because they have the same voltage. So if you take the VA minus VB, it's going to be 0. So no extra energy is required to move a charge along that surface. So those surfaces are known as equipotential surfaces. And if it is a line, then we said equipotential line as noted here. Okay, we'll just solve one or two examples to see how we can determine electric potential given the electric field lines, or how to determine the electric field vector E given electric potential. Okay, in this example, we're asked to determine the electrostatic potential. So again, just like we did for electric fields, so we have two cases. One is inside this sphere, and the other one is outside the sphere. So what is the electrostatic potential V at this point outside the sphere, and what is V inside the sphere at this point? So before we solve this, we have to first determine the electric field vectors. Now, for R is greater than A, right? For R greater than A, the electric field vector E, so we determined that in the, I think in the first or in the second session when we discuss about electric fields. So E is given as rho naught AQ over 3 times E naught times R squared. So this is the electric field vector, and it's pointing along the radial direction AR. If A is greater than, if R is greater than A, the electric field vector is like this, and if R is greater than A or inside, sorry, this is R, sorry. If R is less than A, or if we're inside the sphere, then the electric field vector E is given as rho naught over 3 E naught times R, pointing along the AR direction. So if it is inside the sphere, the electric field vector changes linearly with the radius R. If it is outside the sphere, it decreases with 1 over R squared. So now V, or the electric potential is given as minus E dot dl. So let's say our goal is to determine the electric field outside. So when we determine electric potential, we always start from outside. So our reference point is infinity, let's say. So our goal is to bring the unit charge from infinity to this point. And this point is at a distance R from the center. So our goal is to bring the unit charge from infinity to point R. So let's say this is infinity. So our goal is to bring this unit charge from here to here. So that's our goal. So bring that charge from infinity to this point. So it goes from infinity to this point. Since we are outside the sphere, so let's say this is E1, and let me say this is E2. So E1 is for inside the sphere, and E2 is outside the sphere. So since we are outside the sphere, or our goal is to determine the potential outside the sphere, so this is E2. So this is infinity, sorry, from infinity to R. E2 is given as rho naught R. Sorry, it's not E2, it's E1. Sorry, there is a typo here. So let me erase. So it's not E2, it is E1. So E2 is for inside the sphere, E1 is for outside the sphere. So it should be E1. E2 is for inside. So E1 is E rho naught AQ over 3 E naught R square. And DL is a differential length, so which is, in this case, is dr. We're along the radial direction. So it is dr. So if you integrate these, what do we get? So, or if we integrate this, let me write it here, it's minus rho naught a cube over 3 e naught. These are constant. And the integral of r squared is minus 1 over r. It goes from infinity to r. And minus of minus is plus. And this will give us rho naught a cube over 3 e naught times r. So this is the electric potential for outside the sphere. So if we want to bring the unit charge from infinity to a distance r from the center outside the sphere, then we use this expression to determine v. Okay, now, so this is for r greater than a. What if r is less than a? So in this case, v is, electric potential is, so our goal is to bring from infinity to this point inside the sphere. So that's nothing but from infinity to the surface. Let me use a different color to visualize that. So this is from infinity to the surface, and from the surface to this point. So bringing a charge from infinity to inside the sphere is the same as bringing from infinity to the surface and from the surface to the inside, because we have two regions with different expressions for the electric field. So we have E2 here, and we have E1 here outside. So it will be minus from infinity to the surface, which is A, and we have E1 dot dl plus, and then from the surface to inside. Now in this case we have E2 dl. So this summation will give us the electric potential inside the sphere. So that's why always when we, if we're asked to determine the electric potential, we have to start from outside. So from infinity to the outside, and then from outside to the inside. So this is for the first part, we already determined. So this is the expression. So for the first part, this is minus. So the first part integral is rho naught a cube over 3 e naught. Now instead of r, I would say I'll put a. So we bring from infinity to the surface, so we determine that. So instead of r, we'll just substitute a. Plus integral of ar. E2 is rho naught r over 3 e naught, and dl is dr. So this is minus rho naught over 3 e naught. A cancels this, so this will be square, a square, plus this is also rho naught over 3 e naught. Now r is r squared over 2 from a to r. From a to r. So this is minus rho naught a square 3 e naught plus, now we have r, so rho naught r square over 6 e naught minus a, so rho naught a square over 6 e naught. So therefore, for inside this, so v is, so this one, so for inside v is 1 over 3 minus 1 over 6 is 1 over 6. So this will be minus rho naught over 6 e naught times a square. Plus, again, minus rho naught over 6 e naught times r square. Or if you take rho naught over 6 E naught as a common, so this is minus rho naught over 6 E naught as a common, is A square plus R square. Okay, so this is the expression for the potential out for inside the sphere, and that is the electric potential outside the sphere. So we were able to determine that. So this is one expression for V is out inside. Yes, so this is the expression for V is when R is inside the sphere, and this is the expression when this is the expression when R is outside the sphere. So we were able to determine the electrostatic potential. This is a second example related to electric potential. Now here we're given V. In the previous example, we used the electric field vector E to determine the electric potential. But in this case, V is given, the electric potential. It's a function of x, y, z. So we will be using rectangular coordinate system. And there are two questions. The first one is find E, the electric field vector. And then using that E, we can determine the charge within the cube. So for A, so the electric field vector is given as negative of the gradient of the scalar function V. So, okay, so this is equal to minus partial x of V AX plus partial y of V AY plus partial z along is of V. So now let's determine each. So partial of V with respect to x. Now if you derivate V with respect to x, we'll have 2x y z plus 3. And partial of V with respect to y, now we derive with respect to y of this function. So this will leave us x squared z plus 3. And the last one is again partial with respect to z. Now that will give us x squared times y. So I can substitute these expressions here. So E, or the electric field vector, will be minus 2xy z plus 3 ax minus x squared z plus 3 along ay minus x squared y along az. And the unit is volts per meter. So that's the answer for A. So determine the electric field. So we determine. Now we're asked to determine at specific points. So we're asked for E when x is 3, y is 4, and z is minus 6. So at this specific point, what do we have? So this is minus 2, x is 3, y is 4, z is minus 6. Is along ax minus x squared, x is 3 squared, y, there is no y here, z plus 3 minus 6 plus 3 along ay minus x squared, x is 3 squared times y, y is 4 az. So at this specific point, we have, this is minus 3, minus of minus will be plus 3, 3, 9, 72 ax, again minus of minus will be plus 3 times 9 is 27, AY. So then again, minus 3 squared is 9, 36. Again, this is volts per meter. So at that specific point, this is electric field vector. Now, part B, we're asked to determine the charge contained in this cube, where the cube is 1 by 1 by 1. So using Gauss law, we know that closed surface integral of E dot ds is equal to Q enclosed, or the charge enclosed in the Q, divided by E naught. So we have to determine the surface charge. That's one way. And the other way is we take the divergence and then integrate that with a volume. So this is one way. So from this we can determine Q, or we take the divergence of E, and the divergence of E is equal to rho V divided by E naught. So once we determine the unit vector, once we determine the charge density, then we can integrate that over the entire volume to determine the charge. So there are two ways. You can use both ways to determine the charge. One is take the integral over the closed surface, and that will give you the charge, the total charge. And the other one is take the divergence, and then that will give you the charge density. If you integrate over the entire surface, that will give you, if you integrate over the entire volume, that will give you the total charge. So from this, once you determine that Q is the volume integral of rho V dV. From this, you'll go to the, so the first case, there's one step. In the second case, we have two steps to determine Q. So if I use the first case, Q enclosed, if I use first case, now there are 6 surfaces, right? E dot ds1 plus E dot ds2 plus again E dot ds3 plus, let me erase this part. So because a cube has 6 sides, so this will be over the entire surface. ds4 E dot ds5 plus again E dot ds6. So the integral over the surface. So this is over S1, S2, S3, S4, S5, and S6. So we have Q. So you can define each surface. So what is S1? What is S2? What is S3? So if I, for instance, if I label, let me just label the sides here for you. I mean, you can define it in any way, but let's just say that this is our Q. Right, let's say S1 is equal to, let's say this is X, Y, and Z. So S1 is this side pointing along the, so S1 is minus AY dx dy. S2 is AY dx dy. Let's say S2 is this side. S1 is this side. Let's say S3 is AZ dx dy. So this is AY dx dz. And this is dx dz. And S4 is the bottom surface minus AZ dx dy. And S5 is the sides, which is AX dy dz. And S6 is minus AX again dy dz. So you can substitute these expressions for the E and take the dot product, and at the end it will give you the electric field vector. So we can substitute the values here for each function, and then you can compute the value for Q things. Okay, let's say so the first one is, so at least let me just do it for figure. So E dot ds1. So S1 is along the AY minus AY direction. So E, the electric field vector E, had three components, AX, AY, and AZ. So we will only consider the AX component. So this will give us the EX component times ds1 minus dx dz. Again, surface integral of E dot ds2 will give us the same thing, Ex dx dz, but the only difference is the first one is negative, the second one is positive because of minus y and plus y. And for the second one, you have E dot ds3. Now ds3, if you see, it's along the z-axis, so we only consider the z component. So this is Ez dx dy, and this is E dot ds4 will be again Ez dx dy, but now we have a minus sign here. So you can do like this for the rest. So integral E dot ds5 will be equal to, again, s5 is along the x-axis, so this should be Ex dy dz, and again integral E ds6 will be minus Ex dy dz. So with this way we can determine the value. So there's a typo here. Let me just update that. So there's a typo here because S1 and S2 are along the y-axis. So we should have EY instead of EX. So EY. So you have the expression for EX, EY, and EZ. Plug those values and integrate to get the final answer. Okay, if we substitute the values for EX, EY, EZ and solve, that's what we will get. So for the first surface, for S1, we get this. Let me change the color. So for the first surface, that's what we'll get. For second surface, for the third surface, for the fourth surface, for the fifth one, and the last one. And for the last one, since it is on x equal to 0 surface, then if you substitute that here, if you substitute x with 0, Ex term will be gone. So therefore, there's no integral on that. So therefore, the surface integral of the electric field vector E with respect to S will be the sum of these 6 components. Now we know this cancels out this one, this cancels out this one. So if we add the 3, if we add the 6 component, what we'll have is only 2. So Q is this E dot ds, this closed integral multiplied with E naught. So therefore this is 2 times E naught. That is a charge where E naught is 8.85 times 10 raised to minus 12. So this is 2 times 8.85 times 10 raised to minus 12. If you multiply with 2, then you'll get Q. So that's how we determine. So what makes a difference from the previous scenario is, in this case, we were given V, the voltage, or the electric potential. And from that electric potential, first we determine the electric field vector E. And using, again, Gauss law, we were able to determine the charge Q. Good. Okay, let's go to the third example. So in the third example, we have the potential V, the electric potential, and we're asked to determine the electric flux density D. So we use the same expression. So E is equal to the gradient of V, but D is E naught times E. So therefore D is E naught times minus the gradient of V, or minus E naught times the gradient of V. Now, in this case, we have cylindrical coordinate system because the parameters are R, Q, theta, and phi. So we have to use the gradient expression for the spherical coordinate system. So as you can see on the corner, the gradient for spherical coordinate system is given here. So this is minus E naught times the gradient, which is partial R of V of AR, plus again 1 over R, and partial of V with respect to theta, and that is along the theta component, and partial 1 R sine theta of with respect to phi component. Now let's determine each. The partial of V with respect to R, V is given, so the partial of that, so partial of R of this function, 1 over R cubed sine theta cos phi. Well, sine theta and cos phi are constant, so you can take this outside. So you still have sine theta cos phi. And partial of R cubed is R squared. And there is a minus 2 here. The minus 3, sorry. So minus 3. And this will, it's a derivative, so this will give us sine phi, so sine theta cos phi. And now 1 over R cubed, if we take the derivative of that, that's going to be 1 over R4, and here we have a minus 3. Okay, for the second term, so partial of V with respect to theta, now it's with respect to theta. So 1 over R cubed times cos phi is constant, so we have partial with respect to theta of sine theta. So we can do it this way. This is easy to understand. So this will give us sine theta is cos theta, so cos theta cos phi over R cubed. And the last one is a partial with respect to phi. Now, in that case, sine theta over R cubed is constant, so partial is with respect to phi. And we have cos phi. And the partial of cosine, or derivative of cosine, is a sine, minus sine. So it will be minus sine theta sine phi over R cubed. So therefore, the flux density D is minus E naught times this vector, times this gradient. The gradient is minus 3 sine theta cos phi over R force along the AR direction. plus cos phi over RQ along the A theta plus minus of sine phi over RQ, and it is along the phi axis. So this is the answer. So this is D. So the flux density vector for the given electric potential V. You can take out some of the common terms. So this can also be expressed as D minus E naught over RQ times. So this will be 3, or you can multiply with negative. So minus of minus will be plus, so 3 sine cos phi over R, and this is AR minus cos phi of A theta, and then minus of minus will be plus sine theta sine phi A phi. So this is the electric field, the flux density vector D for the given electric potential V. Now keep in mind that everything is in free space, so we're using E naught. So this is the permittivity of air. Okay, that's all for electrostatic potential. In the next session, we'll discuss about how to determine electric field vector E in the presence of materials. Here also, the other thing is we can also determine the electric potential due to arbitrary charge distribution. Now, if we don't have symmetry, then we know how to determine electric field vector, and then we can use those electric field vector to determine V. So that's one way. The other way is we can also directly solve for V without solving for E. Without solving for E or for the electric field vector, you can directly solve for the electric potential. And how do we do that? We can use these expressions. So these expressions are similar to the expressions we have for electric field lines, but the only difference is, if you see here now, we don't have any unit vector because V is a scalar function. And in the denominator, we only have the magnitude of R, not the magnitude of RQ. For electric field vectors, we had a unit vector AR, or we have R over RQ. But in this case, no unit vector, and R is a magnitude, and we don't have any vector for R. So this is a simplified expression when we have arbitrary charge distribution, and in those cases, we can directly use this expression to solve for V. But we have to be very careful again. For source points, for the charge distribution, we put a prime just to show that those points indicate the charge distribution. But for the field point where we determine the potential, we don't have any prime. So be consistent on these approaches, on these parameters to avoid confusion. That's one thing. And the other thing is make sure that you have the same field point throughout the entire problem. So if you change those the field points, then you have a different R and different vector. But we assume, of course, field point is a point where we want to determine the potential, so it should be fixed throughout our analysis, and our reference point should also be again fixed. So usually we take infinity, but it may not work for cylindrical coordinate system when we have a line charge distribution. But for others, again, we can consider infinity. But regardless of that, make sure that again your reference remains the same throughout the problem.